Can you see my screen? Everybody, can you see my screen?
Yes, we see, Dr. Ali.
Okay, great. So as you can see, we were discussing these numerical problems. So we will continue. I think you all were done number 1 last time, and then answer was 0.858. How about 2? Were you able to complete number 2, everybody? Did you try number 2?
Yes, I did, Dr. Ali.
Okay, so what was the result? There are 2 results. Calculate the moment of inertia of the machine. And then again, second question was, what was the power factor? So what was the moment of inertia value?
I got 20089 for 9. Yeah, 20,089.
20,089. Okay.
0.944.
It looks like when I was doing, I got 20,101.16. Although it is nearby, but still it looks like 11 kg meter square difference.
And I got power factor 0.894.
0.894.
Yes.
Okay. But the J value looks like somewhat. So has anybody tried number 2?
Yes, Dr. Ali, but I got different numbers. For the J, I got 497.9 times 10 to the power minus 9. And for power factor, I got 0.89.
Okay. J value looks like you're pretty strange.
Yes, I don't know why I did it 2 times, but I got the same result. I don't know why. So I would like to review also the values for the RPM. So I got 1,000.
Okay.
Go ahead, sir. I'm sorry.
Okay. So first of all, everybody see the problem. Once again, everybody take your calculator, pen and paper. You see, a synchronous generator is driven by a 5 horsepower synchronous motor that develops a torque of 25 Newton meter. So this means in this case, your synchronous motor is the prime mover. That is the main source. So therefore, for example, just a moment. I mean, it will be like that. This is the synchronous generator shaft. I mean, it is rotating, but this is basically being driven by a synchronous motor. So for example, this is your synchronous motor. So this means synchronous motor shaft and this is generator shaft are common. It is common. They are sharing each other. Therefore, if you can find out the speed of the motor, that is the speed of the generator. Now, this is the relationship, like power equal to the torque multiplied by omega. That's the relationship, where this is in watt and this is in Newton meter. Sorry, Newton meter, and this is in radian per second. This is in radian per second. So that's the thing. So therefore, you see the torque was given, power was given in terms of horsepower. So from there, you will be getting speed in terms of radian per second. And once you get the omega in radian per second, then you convert into RPM. So what you have to do, for example, you got K, just an example, you got the omega value K radian per second. So therefore K multiplied by 60 and then over 2 pi. This will be your RPM value. So therefore, Amani, did you change to RPM? Amani?
Yeah, I did, but I think I did the opposite. So instead of time, do it 60 over 2 pi, I did the opposite. I did 2 pi over 60. I'm sorry about this mistake.
Oh, this means you made much more smaller again. Yeah. So therefore, you see, this is the equation. Everybody.
Yeah, I got something different. Mhm.
Okay. So Sindhuja, can you follow me? Sindhuja?
Yes, Dr. Ali.
Yeah. So first, please write down this equation that forward equal to torque multiplied by the omega. This is speed, but this is in radian per second. This is not in RPM. And this is for synchronous motor. But as I said, synchronous motor shaft means it is the same shaft for the generator as well. They are sharing the common shaft. Therefore, by using this equation, first find out omega in radian per second, and then convert radian per second. For example, you got 100 radian per second. That I mean by the symbol K. And then multiply it by 60 and divide by 2 pi. Then it will give you the RPM. Same thing, for example, you have a speed in terms of RPM, and if you want to convert into radian per second, that time you have to multiply by this and divide by this on opposite. Like Amani, that you did, if you have RPM, then from RPM to convert into radian per second, you have to multiply by 2 pi and divide by 60, just the opposite. Okay, so therefore, so again, I'm going back there. Okay, so therefore from first line, you are getting synchronous generator speed. And then you see the inertia constant is given, which is 2.5. Then calculate the moment of inertia of the machine while it provides 80 megawatt of real power and 40 megawatt of reactive power. And also at what power factor is the generator running. So therefore question is find out the moment of inertia. So therefore if you see this equation, you have to find out J. So therefore you see H is given, RPM you are getting from that omega, and MVA rating, this thing you will be getting with the help of these two. Of the machine while it provides 80 megawatt of real power and 40 megawatt of reactive power. So by using these two information, these two power, you will get the apparent power. Like because then once again, you see, this is that one. Like your P is given, P value, real power, your Q value is given. This is that angle theta, power factor angle. This is your S, apparent power. Yes, so which is P square plus Q square. And then you have to express this on in MVA, and that is your in equation H, like H equal to that how much 5.48 multiplied by 10 to the power minus 9, and then you have at the denominator MVA rating, and in the numerator you have J and RPM square, right? This is the equation. So therefore this S value will be your MVA. So therefore you have the P value and you have the Q value in megawatt and megawatt. Find out S by using this one. That will go in the denominator of this expression. So then you are getting RPM from here. After converting radian per second into RPM, this is 10 to, so finally you will be getting the J as I said, I calculated, I got 20,101 point approximately 16 kg meter square. I got this result. So Kamana, can you check once again? Like you said, you
Sure.
got yes, Kamana.
Yeah, I will check.
Okay, Manoj, did you try?
Yes, Dr. Ali.
So is it nearby? Is my answer correct or I must deviated?
So what was your RPM? 1425?
RPM, I got, yeah, 1424, right? 1425, right? That is right.
Yes, Dr. Ali. Yeah.
Yeah.
Yeah, it was
Got
right
it.
almost.
And then S value here, it is 89.44, this MVA.
Yes. Yes, yes. Same.
Okay, great. So everybody, please follow and try with me. So this should be 89.44 MVA. Okay, and then finally I got J value 20,101.16 kg meter square. Lakshmi? Lakshmi, did you get the same result or different?
Yes, Dr. Ali, I got the same results like RPM 1425.
Okay, and then what is the J value, final J?
Yeah, 21,101 point.
Oh, okay. Oh, great. Yeah.
Yeah.
Okay, thank you. Sindhuja, can you follow me?
And the power factor is 0.8944.
Yeah. Kind of 0.894 approximately. That will be your power factor value. Venkat, did you get all these numbers?
Yes, sir.
Okay, oh great. Yeah. I mean, these are not difficult problem, just you have to write this expression correctly and then you just follow the standard equations, these equations, and then these things. So that's all. And then you all know the power factor. From geometry, you can calculate. So only key to is that you have to write down this equation correctly, H expression. Then you will be getting correct result. So Amani, can you see where you made mistake?
Yes, sir. That was my mistake.
Okay.
When I converted from omega to RPM, I did the opposite. That's my
Okay.
mistake.
So you made
And
much.
I got the same results.
Oh, okay. Thank you.
Thank you.
Okay, great. So therefore, now I am stop sharing this on now. One second. Try number 3 and number 4. 3 and 4. So therefore, similar problems, number 3, number 4, you might have done in other courses, even in your undergrad courses in energy conversion or basic power system or distribution system. In this type of courses you have done. But still, if you think that this is the new, then once again, please have a look. An industrial customer with a 20 kilowatt single phase load desires to raise the power factor from 0.5 to 0.9. So this means that there is a customer, industrial customer has 20 kilowatt single phase load and it has the original power factor 0.5, but power factor is raising up to 0.9. And then if the load voltage and system frequency are 10 kV and 60 Hz respectively, then calculate the capacitance required to correct the load to the desired power factor. So therefore you all know that capacitor can improve the power factor. So in this case, capacitor is improving the power factor from 0.5 to 0.9, provided that the load voltage is 10 kV and frequency is 60 Hz, and that the load active power is 20 kilowatt. So the question is, what should be the capacitance value in farad or microfarad? to correct the load to the desired power factor? That's the question. So therefore, you see the problem, and then once again, let me take you to that whiteboard, so then you will get it. Let me clean up this one, and then you try once again. So I'm giving you the hints, and then you can do that. So therefore, for this type of problem, like first everybody draw your power triangle. So this is phi, this is q, and then this is the theta. And then of course, this is your S, that apparent power. So this is P square plus Q square, that you know. Now, for example, we have a certain value of Q, and that phi equal to that 20 kilowatt. The problem says this is fixed. So now when this is the value of the theta and this is the value of the Q, at that time this is the P. Now with the same P, for example, you inserted a capacitor. Because you inserted a capacitor, so this Q magnitude got reduced. For example, your new Q magnitude is this. So therefore, originally, for example, this was your Q originally. But then now you use the capacitor, and that capacitor reduced the amount of reactive power. And for example, this is your new triangle, this one. So, and then this amount, I mean this distance from here to here, that is your new Q value, designate like Q new. And then this was your like Q old. Old means the previous value. So therefore, definitely you see this portion from here to here, that is being compensated by the capacitor. So that portion is Q cap, Q capacitor. So therefore now what is the thing? So therefore see here, this means that if you can find out what is the value of Q cap, what is the contribution in terms of kilovar or megavar of the capacitor that made a small value of Q, which is the Q new. So this means Q cap is, you see the original value or the old value, this whole distance, that Q old minus this Q new. And first I'm telling you the process. So this means with the help of this triangle, given that this is the 20 kilowatt, you have to find out this Q old value and Q new value. And then if you just subtract, that will give you a Q cap. Now, for example, if you have a capacitor, I'm just telling you the theory, and then if you have a capacitor and it has a voltage VC across it, then what is the QC, reactive power value? QC is VC square over XC. That is the reactive power across a capacitor. And what is that XC? You all know that XC is 1 over 2 pi FC. That is the definition of XC. Therefore, you see, if you can just find out this one, this difference, you just need to find out this magnitude Q cap. And then once you get that value, then you just say, according to this equation, that is your VC square over XC. Yes, and what is the XC? XC is 1 over 2 pi FC. Therefore, everybody see in the problem, this is given VC. How much? This was, I think, 10 kV. This was given. And inside XC, that is 1 over 2 pi FC, You can see C is the capacitor and F is the 60 hertz that is given. So therefore, if you just know this number, Q cap value, what is this amount, and then if you directly apply this equation, then you are able to find out what is the C value. That is the process. Now the thing is that, you see, to find out the Q cap, you need to know what is Q old and what is Q new. This means this one and then this amount. So therefore, with the help of the triangle, this triangle. So therefore, you see in both cases, for both Q old and Q new, this x-axis, this magnitude is 20 kilowatt. So therefore, this means when it was the Q old, there was the theta old value. And when this is the new triangle, then you have a new theta. This is your theta new. Sorry, this is your theta new value, this one. So the thing is that you have to know this information. So if you see the problem, power factor was given. You see, now one second, just a minute. Let me see. Now 1 second, read that statement, then you will understand what I'm. Now read the statement once again. Industrial customer with a 20 kilowatt single phase load desires to raise the power factor from 0.5 to 0.9. Therefore, everybody see, this is the old power factor, 0.5, or the original power factor. Now you are improving to 0.9, and that is that 10 kV and frequency 60 hertz, and I am using that 20 kilowatt that you noticed. So everybody just remember these two numbers. Power factor old was 0.5 and new was 0.9. Now utilize those two to calculate the capacitance value. So therefore, once again, I am going there. So I am doing this one. So everybody see, what is the relationship with respect to the original triangle? This was my original triangle. This magnitude is Q odd, and this is, so what you can write? You can write tan theta volt, tangent, theta volt is, you see, this Q volt value. Look, the original big triangle. Q volt over P. This P is 20. So therefore, everybody say, if you know what is the tan theta volt, what is the, if you know this theta volt value, this angle, then you are done. Because you know the P value, you will be able to get the tan theta volt value, then you will be getting Q volt. This is your main thing, this equation, this is your theory, that Q cap, this amount is this minus this. So I'm trying to find out this value and this value so that I will get the Q cap. So that I'm doing. Tan theta volt is Q volt over P. So how we'll get tan theta volt? See that the power factor was given, original power factor was given 0.5 with respect to this theta volt. So therefore, everybody see, this power factor means which is cos theta volt. This cos theta volt is this value, 0.5. So therefore, this is cosine theta. From here, find out what is the corresponding tangent theta volt from here. And then what is the new power factor? New power factor is 0.9. This means your cos theta new is this value, this number, 0.9. This means with respect to this small triangle, with respect to the new triangle, this angle is theta new. That you are getting from here. Then similarly, you write down another thing, another term. So let me clean up this thing. You write down this thing. This means tan theta new. Again, what is that? Q new. Q new over P. Similar to this one. So therefore, again, P is 20 kilowatt. you are getting tan theta nu from here. This is the cos theta nu value. From here, first find out theta nu angle and then find out tan theta nu, and then plug in this equation. So you will get Q nu this one. From this, you will be getting Q word, and then you subtract. That will be your Q cap. Apply this equation. Use X is 1 over 2 pi FC, and finally get the value of C. How much C you are getting? Everybody, could you follow me?
Yes, sir.
Yes. So are you calculating? Everybody, please calculate.
Yeah, what was the C?
C is the capacitance value.
No, no, no. What is the answer for the C?
Oh, okay, okay. So answer should be 0.663 microfarad.
Yeah, I got the same one. 644 something like that. But yeah, sounds
663 microfarad.
right, right.
Yeah, I also got the same, Dr. Ali.
0.663 microfarad.
Mhm.
Yes,
Okay,
0.66.
very good, very good. Sindhuja, could you follow me?
Yes, yes, Dr.
Yeah, I think, I mean, you easily understand this triangle. Yeah. So therefore, once you see the power factor improvement problem, then please use this triangle. I mean, remember, this is called power triangle. So just with the help of geometry, you can solve the problem. Just remember this thing. So therefore, everybody makes sure that finally you are getting capacitor value 0.663 microfarad. Yeah. And then VC was 10 kV. Remember, it was 10, not 10 volt, 10 kV. And the next is 1 over 2 pi FC. And F was given 60 hertz. F value was 60 hertz. Sorry. Lakshmi, did you get a result?
Yes, Dr. Ali, I got 0.662 microfarads.
0.62 microfarad. Okay.
662, yeah, only one digit.
Oh, okay, okay, okay. Okay. Venkat, did you get?
Yes, sir.
Okay. Then Amani, were you able to solve?
Yes, Dr. Ali.
Okay. Okay. So therefore everybody is fine. So because I saved, so you can see in the video once again. Okay. Great. So now go the next problem, and then there are much more questions. Everybody say read number 4. A three-phase 12.0 kV 60 Hz two-pole Y-connected cylindrical rotor synchronous generator has a synchronous reactance of 3.0 ohm per phase. If the internal generated voltage is 15 kV and power angle is 30 degrees, then calculate the torque of the generator, reactive power provided by the generator, also the power factor. Here there are 3 questions: torque of the generator, reactive power provided by the generator, and the power factor. So you see what information is given. This is the terminal voltage 12 kV for the 3-phase system, and it is Y connected. Keep in mind, it has synchronous reactance, that is the XS value 3 ohm per phase. And then this is the internal generated voltage. And the power angle is 30 degrees. So therefore, for this problem, so everybody, you see this one. This is the relationship among the internal generated voltage, terminal voltage, and the phase angle or the torque angle. So everybody see this equation. P equal to 3EA V phase over X sine delta. Therefore, in this equation, the delta is the torque angle, and at the denominator, Xs is the synchronous reactance. And in the numerator, 3 is multiplied because this is 3-phase. So therefore, because 3 is for 3-phase, definitely EA and V phase, these are the phase voltage. everybody keep in mind in this equation that EA and V phase are the phase voltage. So V phase, second term, this is the terminal voltage. You note down in your note, V phase is the terminal voltage. And EA is the internal generated voltage. I mean, I have defined it here, internal generated voltage. But keep in mind, everybody, that EA and V phase, these are the phase voltage, not the line-to-line voltage. I mean, the equation is for three-phase system, but because EA and V phase are expressed in terms of phase quantity, that's why it is multiplied by 3. So therefore, everybody write down this equation, phi, and then everybody write down the last expression for Q. Please write down this on Q as well. This means if a system has the internal generated voltage, terminal voltage, then the reactive power can be expressed by using this equation. So therefore, please note down this P real power equation and the reactive power equation in your note. So, and then these two equations are just showing what is the P max value. You can see because it is sine delta, so delta value can be maximum 90 degree. So that's why this will be the P max. Similarly, this is the torque max, that P max over that omega m in radian per second. So therefore, you know these things. Just you write down the P equation and then the Q equation. So everybody, have you written down? Write down this one and this one. Then I am going to that numerical problem again. Are you done? Have you written down P and Q equation?
Yes, Dr. Ali.
Okay, everybody?
Yes, Dr. Ali.
Dr. Ali.
Okay, thank you. So then I am going to that problem. Now, see, read number 4 and then use those two equations. So you see that 12.5 kV, this is the terminal voltage of the synchronous generator. But keep in mind, here this 12 kV, because this is three-phase system, this is line-to-line voltage. This is not the phase voltage. So what you have to do to use that equation, because this is Y-connected system, so you have to divide this number
Square root 3.
square, yes, root 3. So therefore, everybody, you have to divide this number by root 3. Same thing, this is the internal generated voltage 15 kV, because it does not say that it is single phase. So by default, this is three phase because the original system is three phase. So again, you have to divide this number by root 3 as well. So this means everybody, both this terminal voltage and internal generated voltage must be divided by root 3. And the synchronous reactance is 3 ohm. Your power angle, this is the delta in that equation, which is 30 degrees. So therefore, based on that, first you will be getting the P value. First you will be getting the P value. And once you get this result, then you just divide by the omega. So therefore, you will be getting omega from here, 120F over P. 120F over P, that will be RPM. And you have to convert that into radian per second. Then you will be getting the torque. So the first answer that you are asked to calculate torque of the generator. So therefore, first find out P value, then calculate the torque. Then find out the reactive power by using the other equation, this equation. And then finally find out the reactive power, the power factor. 3 questions. What was the torque, reactive power, and the power factor? and then let me know what number you are getting. So everybody please try at your note.
Dr. Ali,
Yes?
I have a different value for the voltage, for the terminal voltage. I have 13.2. When I print out the
Oh, okay,
class.
okay. So later, sorry. Later I change this number. So I will be uploading again this updated slide. Yeah.
No problem. It will be the same process, but different values.
Oh, yeah. So therefore, please change to 12. Yeah.
Okay, I will change it to 12 right now.
Yeah, please change 12. Yeah. Oh, yeah, okay. Well, later I changed 12 to get a good number of the reactive power. That's why I changed that number. Yeah.
So the power is 30 megawatt. Okay, we have
P value is
torque.
30 megawatt. Right. That is right. Yes.
Okay.
So everybody, so as you see, the Manoj said the P value is 30 megawatt, which is right. So therefore, the first question is, Manoj, find out what is the torque of the generator. So therefore, again, the torque equal to power over omega. Power over omega. And then let me know what value you are getting. So everybody got the same number, P value 30 megawatt.
I have 32.5 megawatt, Dr. Ali.
Sorry?
I have 32.5.
Megawatt?
Yes.
Did you divide by every number by root 3, this 12, 15?
Yes. I did divide by root 3.
Okay. And then sine delta value is 30 degrees, and then synchronous reactance is 3 ohm per phase.
Yes. And then you need to multiply the numerator by 3, right?
Yes.
Yeah, that's what I did. I got 32.5 megawatt.
So it should be exactly the 30 megawatt.
Okay, let me double check that.
Yeah, please check. Yeah. Lakshmi, did you get the result? P value 30 megawatt?
Yes, doctor, I got 30 megawatt.
Okay, great. Yeah. Sindhuja, can you follow me?
Yes, Dr. Ali.
So are you getting the same number, 30 megawatt?
Yeah. Yes.
Okay, great. Yeah.
So the torque is almost 79.577 kilonewton meter.
79.7 kilonewton meter, right? Yes. Kilonewton meter, that is right. Like I expressed in meganewton meter, like 0.0798.
Oh yeah.
Yeah. 0.0798 meganewton meter.
మరి P వస్తే ఒమేగా ఎలా వస్తుంది?
Sorry? What you said, Kamana?
No, it
I
was
didn't
not
say
clear.
anything, Dr. Ali.
Oh, like who said?
But I also got 30 megawatt.
Oh, okay, that is fine. Yeah. Therefore, and then the torque value, Kamana, did you calculate torque?
No, I'm calculating that.
Oh, okay. So, okay, then Manoj, keep going. Now you calculate the reactive part. I mean,
Sure, doctor.
Three portions: torque, reactive power, and then power factor. 3 questions. Uthman, did you get the correct result now?
Yes, I got, Dr. Ali.
Oh, okay. Maybe some calculator mistake or
Yeah.
something. Yeah. Okay. But the question is find out the torque, Uthman. From the power, calculate the torque.
Yes, I'm doing that, Dr. Ali. I'm calculating this.
Okay.
Dr. Ali, what is the value for Q. What is the answer for Q?
Q value 3.96 megavar.
Yeah, I got that.
3.96 megavar.
96.
Okay, great. And what was your torque value?
No, I have not calculated.
Oh, okay. Okay.
I'll do so.
Yes. From the power value, you just need to divide by the omega in radian per second. Then you will
Yes,
get it. Yeah. Did any other calculated the Q value? As Kamana said, she got 3.96, which I also received 3.96 megavar, the Q value, reactive power value. Lakshmi, did you get the Q value?
I'm doing, Dr. Ali.
Okay. Amani, did you get Q value?
Oh, not yet, Dr. Ali. I'm still working on it because I got different numbers, so I start over. So,
Oh, okay. No, I'm sorry. So use the 12. Yeah. Use
So
the
what is the answer for the Q value?
3.96 megavar.
Okay.
Kamana got the right result.
Dr. Ali, I got torque value 1.52 mega. Newton.
No.
Is this right?
Mega Newton?
Yes.
No, it should be 0.0798 because Manoj calculated, like he said, 79.8 kilonewton meter. That's correct. I expressed in mega. So maybe you messed up with the radian per second conversion.
I got 19.739 radian per second. Is that right?
No, that's wrong. How you get that? First calculate the RPM. 120 F over P, so that is your 3600 RPM, and then convert that RPM into radian per second. So radian per second should be 376.99. I mean, almost 377 radian per second. The angular velocity, omega value.
Yeah, I got 3.9615 megavar.
Yeah. So that's right. Yeah, Q value. And then finally calculate the power factor. Manoj, there is one more question, power factor.
Sir, I got 3.961 mega.
Megavar, yeah. And Venkat, what's your torque value?
Torque value? I'm calculating it.
Oh, okay. And did you get power value 30 megawatt?
Yeah, yes, sir.
Okay, so from power value, calculate the torque value. You may express either in meganewton meter or kilonewton meter. Sindhuja,
Sir, how to calculate omega m, sir? Once can you push?
no, first you'll see the very first line of the problem, 60 hertz and 2 volt. So first find out the synchronous speed, 120 f over p.
Yeah, that is done, sir. After that,
After that, you have to convert into radian per second, multiply by 2 pi and divide by 60.
okay, yeah, I got it.
Yeah.
Sure.
So 120 f by p, that is expressed in RPM.
Okay, that is into 2 pi by 60, right?
Yeah, 2 pi by 60.
Yes.
So I got the power factor of 0.9914.
Yeah, that's right. Yeah, I'm pretty close to 1, so that's all right. So you are fully fine. Sindhuja, are you getting?
I'm doing, Dr.
Okay, take time, everybody. Yeah. Lakshmi, did you get Q?
Dr. Ali,
Yes?
is the torque value 1745 Newton meter?
No,
Oh,
like it should be 0.0798 meganewton meter,
okay, I got.
or in kilonewton meter, 79.8.
Oh, okay. I will retry.
Yeah. So you got the power value 30 megawatt, right? Yeah.
Yes, Dr. Ali.
So then you just need to divide that number by the omega in radian per second.
Oh, okay, Dr. Ali.
Yeah. So therefore, you see the problem, the very first line, 60 hertz to volt. So from there, you calculate the synchronous speed first, 120 f over p. That will be in RPM. Then you convert into radian per second.
Okay, Dr. Ali.
Yeah, maybe like you have missed that part.
Yeah.
Yeah, that's why you got completely different number for torque.
Yeah.
Okay.
Dr. Ali,
Yes.
I still have a different numbers, so can you please give me the values for the internal generated voltage after divided by square root of 3? Because I did it 3 times, but I still have different number. So
Are you talking about the Q?
yes, sir.
What result did you get?
Okay, for internal generator voltage after divided by square root of 3, I got 8,660.
So you
Volt.
divided it 15 over root 3, right?
Yes, sir.
And the terminal voltage 12 over root 3. Terminal voltage?
Yes, sir. I
Okay.
got 6.93.
Okay. So and
So
then
this is my values. So when I plug them in the Q equation,
okay.
I got different numbers. So I'm trying to find where is my mistake. I did it 3 times, but I got completely different numbers.
Okay. So therefore, look once again the Q equation. Did you multiply by 3?
Yes, sir.
You see, and then in parentheses, EA V phase cos delta. This is minus V phase squared. Did you?
Okay. V square is 48. The number is 48.
This is like 12 over root 3, then square. 12, it will be 12 over root 3 kV.
Yeah. And I got, for this, I got 48.
Okay, so I mean, when I calculated, I did not write the result, but in this place, did you use the 12 over root 3 kV squared?
Oh, yes, sir.
Okay, and the next is your 3.
Yes, sir.
So therefore, it looks like you put correctly, but then somewhere maybe in your calculator you are getting
I
different.
think so, yeah, because I did it 3 times, but I still got completely different numbers. I will try to do it again, start
Yeah,
over
yeah,
one more
yeah,
time.
yeah.
Yeah.
That's together.
But I got the idea, I got the process.
Yeah, yeah. I think you got this one. Yeah.
Mhm.
Maybe just it's the matter of your calculator. Yeah.
Yes, sir. Yeah.
Maybe calculator is not helping you.
Yeah, it's new calculator because my old one, it's the battery is die, so I used one new one, so I need to use it more and more to get familiar with this one. Maybe that's why.
Okay. Got it. Also make sure that when you are using that cos delta, it is not in radian mode. It should be in degree mode.
Mm-hmm.
Yeah.
Yes, sir.
That may give you the different result as well.
I think so, yeah, because my answer completely different than yours.
Yeah. Probably your calculator is giving you the wrong result.
I think so. Thank you.
Dr. Ali,
Yeah.
I got power factor 0.99.
Okay. And what is your torque value?
0.07 Newton, mega Newton meter.
Mega, yes, right. That's right. So then you are fine. And you got Q value 3.96, right? Megawatt.
Yeah.
Okay. Then fine. Lakshmi, now did you get the correct value for torque?
As Dr. Ali.
Is it 0.0798 mega Newton meter? Or 79.8 kilonewton meter?
As Dr. Ali, I got it and I'm doing power factor.
Oh, okay. Fine. Venkat, Sindhuja, are you fine so far?
Yes, sir.
Okay.
I got the torque value. I'm working on power factor.
Oh, okay. Sindhuja?
I got the Q value 3.958.
Yeah, that's right. 3.96. And then what is your torque value?
I'm working. I didn't get it yet.
Oh, okay. So for the torque, like power over omega is in radian per second. So your P value is 30 megawatt, and then omega is your synchronous speed that will come from that 60 hertz and two-fold first 120 F over phi. This will give you in RPM, and then you have to convert into radian per second by multiplying 2 pi and dividing by 60. Then you will get the torque. Torque equal to power over omega, and omega is in radian per second.
Thank you, Dr. Ali.
Okay, so please keep going. So therefore, everybody, the power factor answer should be 0.99. Amani, did you try power factor?
Yes, Dr. Ali, I'm working on it.
Oh,
But I'm
yeah, but you got the Q different value, so you will get the different power factor.
Yeah, but because of that, I use the appearance power equation, and also I tried to use reactive power equation, but I got 0.9990.
Oh, okay. So that is fine. That is the power factor.
Mm-hmm.
Yeah, I too got 0.99, sir.
Oh, okay. Then that's correct. Yeah. So therefore, Lakshmi and Sindhuja, once you get P value 30 megawatt and Q value 3.96 megawatt, then just use that power triangle. Like tan theta is P over Q. And
Yes,
from
Dr. Ali, I got 0.9 in power factor.
oh, okay, that would be great. Okay. Okay, Amani, then you like keep going. Again, you keep trying that Q by your calculator. Sure, because you know the procedure, you understand the process, so you are fully fine.
Yes, sir.
It's the matter of calculator. Okay, so therefore, everybody, I am now scrolling the next slide. There are a couple of more questions for you. You see, there are some theoretical questions as well that I'll be discussing. Then once again, everybody do number 5. Calculate the stored energy of a synchronous generator at rated speed while it provides 80 megawatt of real power and 40 megawatt of reactive power. Assume the inertia constant of the generator is 2.5. So in this case, I am asking the stored energy. So far, I did not ask the stored energy. So far, I asked like moment of inertia or the MVA value, H value, etc. But in this problem, I am asking the stored energy. Provided that the real power, reactive powers are given, and the inertia constant value is 2.5, that is given.
I got 224. What?
Just a moment. Stored energy?
Yes, sir.
Just a moment.
Yeah, I also got the same result.
200?
Yes, sir. 224.
200 megajoule.
I got 223.6.
Yes.
Yes, same.
Yes. 223.6. Yes. Okay, so then you're fine. So this means that you will be simply using, the very first equation. You don't need to use this equation. You see this big equation because it involves the J. So simply use the basic definition of H. H is stored energy over MVA rating. So then H value is given, MVA rating you can calculate, just multiply. That will give you the stored energy. Could you follow me, everybody?
Yes, Dr. Ali.
Yes, Dr. Ali.
Okay, thank you. Everybody just use the first equation, basic definition.
So it is 223.60.
60 megajoule, yes, or megawatt second or megajoule, right? Yeah.
Megajoule.
Yes, just use this equation. Yeah. Because if you use this equation, then you are not getting the J value. Okay, sorry. So therefore, everybody for question number 5, answer would be 223.6. Okay, so therefore, before discussing number 6 and 7, so that is the theoretical part I need to discuss. Then please everybody jump number 8, and then I am coming back 6 and 7. Once you do 5, then please go number 8. Everybody read number 8. So in this case, what I'm saying, a 2-pole 60 Hz synchronous generator is driven by a 100 megawatt steam turbine as shown in the following figure. This is a synchronous generator. Its turbine capacity is 100 megawatt. Here it is electrical output, and then through transformer, it is going to the transmission line. So therefore, just concentrate on that synchronous generator portion. 100 megawatt steam turbine. That is the prime mover or input to the generator. And I'm saying, assuming no loss of the turbine generator system and the unity power factor for the generator, calculate the moment of inertia of the machine while the generator inertia constant is 2.5 seconds. So I'm assuming that this generator is lossless, there is no loss. And power factor is 1, power factor is unity. Based on that condition, what should be the moment of inertia value, provided that the h value is 2.5 seconds. That's the question. So therefore, again, in this case, because you are asked to calculate the moment of inertia, definitely you will be using that last equation, h equal to this. Now, you need to know that MVA value, MVA rating. You can find the RPM. You have to find out J value, H value just given. So you need to find out that MVA. So you see how you will get that MVA. This is the input to the generator, 100 megawatt. So therefore, because the system is lossless, there is no loss, and power factor is 1. So definitely output power is also 100 megawatt, and output MVA is also 100 because the power factor is 1. So therefore, in this equation, MVA rating, MVA value is 100. Everybody, could you follow me what I said?
Yes, Dr. Ali.
You see, like I am asking the problem a different way as compared to other problems that we discussed so far. Like I'm using this diagram. This is the turbine input 100 megawatt. So that typically every generator has some loss. So definitely output will be less than the input, maybe 80% or 85% efficiency. But in this case, I'm assuming no loss, 100% efficient. So therefore, your output is also 100 megawatt. But then in that equation, you need the MVA, not the megawatt. So meaning that you need to know the power factor value. And that also I have said unity power factor, meaning that power factor is 1. So this means ultimately this generator capacity in terms of MVA is 100 as well. And then you know the H value. So therefore, and then you are getting RPM information from here, 120 above RP. Then find out the moment of inertia. This means find out the J value. So everybody please calculate the J value. And then let me know how much you are getting the J value. Are you calculating J value, everybody?
I got 3520.
3520.1 kg meter square, right? Yeah.
Yes, Dr. Ali.
Oh, great. And that's right. 3520.1 kg meter square. Yes, correct. Manoj, did you get the same number?
I'm doing it.
Oh,
Dr. Ali.
okay.
Yes,
Aman?
Dr. Ali, I got the same as 3520.1 kg per meter square.
Okay, great, perfect. Yes. Amani?
I'm still working on it, Dr. Ali.
Oh, okay, fine. Then Sindhuja?
I'm working on it, Dr.
Okay,
Ali.
okay. I mean, you
I
understood.
got the answer.
Sorry,
I got 3520.
Oh, okay, great. Yes, that's the right 3.2 3520.1 kg meter square. Right.
Yeah, some 1.13 sort of thing.
Yeah. So that's right. Yes. Okay.
Yes, sir.
Okay.
Yes, Dr. Nada, I got the same one.
3520, right?
Right.
10 kg meter. Okay, right. Yeah. So the you see only difference as compared to other problems. Here I am telling a different way. Generator MVA is not directly given. Rather, I am saying in that way that it's a lossless system. Power factor is unity. Then turbine input is given. Turbine input value is given. But then synchronous machine rating means basically the output rating that you have to find out. That's why only this part is the tricky part, or that part is the only the new as compared to the previous problems. So therefore, I hope everybody will be able to solve similar problems in the upcoming midterm exam. Othman, are you getting the results?
Yes, Dr. Ali.
You got the same result?
Yeah, for J, I got the same.
Oh, okay. Right. Okay. Sindhuja, you are still working? So probably you can follow that, Sindhuja. I'm talking for you that moment of inertia means like you are finding the J value, this number, J, this parameter from this equation. Amani, did you get?
Yes, Dr. Ali, I got the same answer.
Okay. Sindhuja, are you still calculating?
Got it, Dr. Ali.
Sorry, what you said? Did you?
I got it.
Oh, the same number? Yeah.
Yeah.
Okay, great. Yeah. Okay, so therefore everybody is done. These are pretty vital and then pretty standard numerical problems. Okay, so now moving forward, is everybody read question number 6 and question number 7. I think the new to you. Question number 6, can a photovoltaic PV system or PMSG, means permanent magnet synchronous generator based wind generator, be represented as an STATCOM with a view to augmenting the stability of a grid connected network? Then explain your answer. So meaning that, so everybody remember that other class I was discussing you the application of DQ0 transformation for control of STATCOM. So therefore, everybody see the topmost side, this portion is actually the STATCOM. So therefore, everybody look carefully. STATCOM means it has a capacitor at the rightmost side. I mean, a small value of capacitor. That capacitor value typically in the microfarad or millifarad range, not large value. And then there will be a voltage source converter and there will be a transformer. So therefore, this is the configuration for the STATCOM. A capacitor, voltage source converter, and a transformer. This is the STATCOM. Now, what question is being asked? Can a photovoltaic system or a PMSG based wind generator be treated or be represented as an STATCOM with a view to augmenting the stability of the grid connected network? It is saying the stability because this is STATCOM actually control the reactive power of the system and hence improves or augment the stability for the grid. So that's why that can you find any similarity that PV system or PMSG can be treated as STATCOM? Therefore, to answer that question, you just need to think about the construction of the solar system and then that PMSG based wind generator, just the construction. Then you will get the answer. Therefore, let me take you to that whiteboard, then you will understand. So that, let me erase these things because I already saved those. Okay. Okay, so I'm done. So everybody say that the first of all, the solar PV system, solar photovoltaic system, how does it look like? So therefore, in case of the solar PV system, you all know that there is a solar panel. This is that solar panel. And then there is terminal head. This is plus minus. I mean, this is DC because that PV solar panel produces the DC, and then right after that it has DC to DC conversion. It is called DC to DC boost conversion because typically the voltage is smaller here, like kind of around 100 volt, 150 volt, not more than 200 volt here. Hardly it is 200 volt here. That's why you need to boost off. So this is called DC to DC boost converter. And then right after that, there is a capacitor, which is called the DC link capacitor. And after that, so this means until this portion, still it is DC. And after that, there is a inverter, but that is VSC based voltage source converter based inverter. This component is called the inverter, but voltage source converter based. This means then you are converting into whether it is single phase or the three-phase system. And then you have a transformer. And from the transformer, you are connecting it to the grid. So this point is the grid. So therefore, this is the basic structure of that solar PV system. Therefore, everybody look the component. You have the PV terminal here, then right after that DC to DC boost converter, then that DC link capacitor, and this is the voltage source converter and transformer. Therefore, you see, you have three components. Look just this portion. That DC link capacitor, voltage source converter, and transformer. This is transformer. These three components together can be treated as a STATCOM. That is the meaning of that question. Therefore, yes, the answer is yes. The PV system can be considered as a STATCOM because it has all the same component, similar component as to the STATCOM. STATCOM has this one, this component and transformer. Same thing, PV system has these three components. So it can work as a STATCOM, meaning that this portion you can treat as a reactive power compensator. When there is any disturbance or any fault in the system, in the connected grid system, then you can utilize these three components together as a STATCOM. That is the meaning of that question. Therefore, like I am saving and then again I am going there and I am coming back. I mean, see the question, read the question again. Question number 6. Can a photovoltaic system or a PMSG base be represented as an STATCOM? So the answer is yes. I mean, so far I discussed PV system. Now I will be discussing the PMSG structure. Then you will get it. So everybody, could you follow me what I am saying?
Yes, Dr. Ali.
Yeah. Therefore, you will be asked this question: can PV system is equivalent or it can be treated as an STATCOM device? The answer is yes. That I mean, that explain. Then you will be telling that, okay, typically an STATCOM has This capacitor, VSC and transformer, the same thing goes for the PV system. It has the similar structure. So it can be used as a STATCOM with the view of augmenting transient stability of the connected grid network. Now look the PMSG structure, then you'll be understanding. For the PMSG based system, okay, let me just erase this thing. So I will get a space here. So in case of the PMSG based wind generator system, basically this is a synchronous machine. It is called that PMSG. Then of course, as you can guess, this is connected to, wind turbine system. It is connected to wind turbine. This is the shaft. And then it is producing three-phase power. And easily you can guess, because the wind speed here is like not constant. Wind speed is varying in that nature. Consequently, you will get varying output here. So you cannot directly connect this onto the grid, because customers will get fluctuated output power voltage. So what you have to do at first you have to convert, definitely, this is AC. This PMSG output is AC. So first you convert that AC into DC. How you will do that? With the help of the rectifier. So therefore this body is rectifier. This is rectifier. So you all know the function of rectifier. So it converted into DC. So here it is DC. But then to hold the constant DC, you need a capacitor here. You connected a capacitor here. Again, this capacitor is very similar to this capacitor, typically in the microfarad or millifarad range, not the big value. Therefore, it was AC here, but until here it is DC. But then again, the grid system is the AC. So you need that inverter here. Therefore, and that inverter here, again, the voltage source converter based. This is your inverter. And then again, to connect to the grid, you need that three-phase transformer. So again, you have the transformer. And then finally, you connect to the grid point. Therefore, see, this portion is again exactly similar to the PV system. That DC link capacitor, voltage source converter, transformer. Same thing here. There is DC link capacitor, voltage source converter, transformer. Just before this, there is a rectifier. Instead of the rectifier, it was in this case DC to DC boost converter, because it is the DC from the beginning. In case of wind generator, permanent magnet synchronous generator, it is AC here. That's why first you convert into DC. So therefore now it is independent of frequency. The goal of converting AC into DC, now it has no frequency component. But then you have to convert into AC, because your ultimate goal was to provide AC, and the grid is really the AC. That's why again you need the inversion. So therefore what I am saying, therefore we will not be studying extensively that PMSG based wind generator system. But if you see the component, again, this structure, these three components constitute the STATCOM. Therefore the answer is yes, PMSG based wind generator system can be represented as STATCOM because it has the similar component. Therefore, definitely with the help of sophisticated control means, you can control the reactive power just by controlling here this portion, and this portion is the STATCOM. So therefore the answer is yes, both PV system and PMSG based wind generator system can be treated or can work as STATCOM. That's the answer. Could you follow me, everybody?
Yes, Dr. Ali.
Okay.
Yes, Dr. Ali.
Okay, fine. So therefore now I think I will be just discussing one question, then we will be done for today. Everybody see question number 7. I think you have never ever heard this one. What is coherency of synchronous generators in a power network? and explain its significance in a large power network. Because we are studying the stability in this course, we are looking the impact of various parameters, various concepts on the stability, like for example the impact of H, inertia constant, and then other parameters, synchronous reactance parameters. Similarly, coherency is a concept which is related to stability as well. But what is the meaning of coherency of synchronous generators? Explain its significance. So therefore, coherency means, again, like for a minute, I will take you to that board. Let me quickly erase all of these things. So therefore, in a minute, you will be understanding and we will be done. So for example, in real practice, it is not just one generator. There are multiple generators in an interconnected system. For example, this is one generator. Just an example, generator number 1. Then there is another generator. And then they are not at equal place or not at the equidistance even. And then, for example, there is other generator head. And then some generators, for example, in this portion, for example, G4. In that way, there are hundreds of generators. This is G5. And then, for example, there is another here. Okay, G6 number. Now, assume that although they, and then, for example, this is the grid point, like this is connected here, this is connected here, this is connected. Assume that all are connected somewhere. Of course, in between there are the other lines, but assume that they all are connected at a common point. Now, easily you can understand that while you have only one generator, and then versus while you have the 6 generator, definitely analyzing the 6 generator is difficult as compared to single generator. If you are asked to find out the load flow, power flow, for example, PQ, or the voltage, or that delta power angle that we are looking to find out at this bus. So when you have only one system or 2 generator versus when you have multiple 100 generator, definitely you can guess with the rise of the, or with the increase of the number of generators, the complexity increases, definitely. This is the natural thing. Now, if you can apply a technique, can we make some cluster? Can we make some group? Then, for example, you discovered a technique. Now, let's make a group. These 2 generator one group. Now, I'm telling that what is the criteria to make group? What is the condition I'm telling? And then, for example, this 3 generator is on group, and this is on. It is not any group, but what is the benefit? You can treat this group as a single big generator. For example, generator J. These 3 generator, you can treat this another big generator. For example, generator number B, this is generator number A. And then this is on single generator that is not in this group, nor in this group, separate. But it's still like it is helping my calculation because I can treat that these 2 is equivalent to one big generator, this 3 is equivalent to one big generator, and this is on. So you can say that now I have only 3 generator instead of having the 6 real generator. This making group of generators is called the coherency, coherent group of generators. So now the question is, what is the criteria? So the criteria is that you will be looking to make it before making the group. You don't know that how to group. Before making the group, first you will be plotting their rotor angle. In fact, that power angle, that thing today we are looking, that delta versus T. Then you plot it for all generators. For example, for generator, just an example, like it is going in that fashion, just an example. For generator 2, it is going in that fashion. Therefore, just a level. This is for generator 1, and then the other one was for generator 2. And then gradually you are plotting, but then for example, generator 6, it looks like it is like that. So you can see it is like deviated, the G6. Then you plot G4, G5, G all three. It looks like, okay, there is close by G6, another is close by G6. So therefore, you will be noticing that the which are swinging, whose power angle is very close, typically like within 5-degree distance. Like one is going in that way, other is also pretty much similar. The distance is from here to here only 5-degree angular distance. That will you can treat as a coherent group. So therefore the definition of coherent means the generators which swing, which run almost together, keeping an angular distance, keeping that power angle value within 5-degree. Those group you can treat as a coherent group. So meaning that now it is not necessarily that only because G1, G2 was in this side, so you will group. It may happen that this G1 is forming group with G5, just an example. A G3 is forming group of G4. You have to look that delta versus T curve, rotor angle or power angle curve. The machines which will swing almost together, almost close by, can be treated as coherent group. Now, for example, that G1, G2 on group, just an example, and then this is on group. So I got the second group. So I can say I have one big machine, second big machine, and this is not any group. The benefit of this method, it will reduce your computational burden. This means that you will be treating their inertia together. Like it has one inertia, H1, it has another inertia. You just sum them up. And then you say, because this is my new GA system, it is coherent group, I have one combined inertia. By assuming that, you find out, you calculate power flow, everything, that will be very, very close to the original system. This means that concept of coherency or making coherent group will reduce your computational burden, and it will behave, its characteristics is very close to the original system. For example, in real practice, there can be 100 generators, but you can group them only into 5 or 6 or maximum 10. So therefore, if you do, when you will be simulating it or you will be making any software for that system, that will make your life easy. That will save your time. It will reduce as the computational burden and computational complexity. Everybody, could you follow me?
Yes, Dr. Ali. Yes.
Yes, Dr. Ali.
That is the meaning of that, concept of coherency. Soon I'll release you. Yes. Now see the question. What is coherency of synchron in a power network? So therefore you will be answering the coherency means clustering or grouping together based on their rotor angle or the power angle. The machines in an interconnected system which swing together, which runs by maintaining that angle of 5-degree, within 5-degree, those are called the coherent group. And when I'm saying explain its significance in a large network, you can say we can reduce a large power network into a reduced order system, and that will save my calculation. It will make easy the calculation, reduce the computational burden, and which will behave almost equal to the original system. So that's why, the concept of coherency is very popular in power network. I mean, really in interconnected system, there are more than even 100 generators. But then you can group them, you can cluster them, you can make only 5 group or only 10 group or even much less. And then based on that, you make calculate versus when you have really 100 generator and you simulate 100 generator, still you will get the very similar or very close by result. That is the benefit of that coherency. Okay, so with that, today I like to conclude here. Like we're almost like 7, so I'm stopping this one.